The research paper presents a novel approach to constructing ab initio nucleon-nucleus optical potentials using the Green's function approach and the symmetry-adapted no-core shell model. This method resolves the issue of spurious center of mass motion by utilizing the Lawson procedure. The authors demonstrate the effectiveness of their approach by illustrating elastic neutron scattering off the 4He ground state, showing remarkable agreement with experimental values. The method provides a tool for first-principle predictions of cross-sections for elastic neutron and proton scattering, as well as for constructing null optical potentials for neutron-proton capture reactions. The authors also discuss the calculation of the effective potential for nuclear reactions using the single-particle Green's function in the shell model with nuclear corepolarization approach. This method addresses the center of mass motion of the target and hole states using the Lawson procedure. The approach is based on the calculation of the SPGF in laboratory coordinates, using the layman representation to eliminate CM spurious effects. The authors of the research paper utilize Jacobi coordinates to express overlaps in both laboratory and Jacobi coordinates for spatial degrees of freedom. They define the Jacobi coordinates, xi underscore a, and xi, which describe the relative distances between the center of mass, cm, of the target and projectile, and the cm of the a+1 system. The laboratory coordinates, r underscore a+, are related to the Jacobi coordinates through equations 15. The authors then express the overlaps of equation 14 in the laboratory frame for general eigenfunctions of the A and A+1 nuclei, defining the cluster basis states for the spatial degrees of freedom. These states are anti-symmetrized to ensure the Pauli exclusion principle. The overlaps are then expressed in Jacobi coordinates using equations 16 and 17. The authors also express the overlaps for the A1 system, which are similar to those for the A+1 system. They then define the Green's function terms for spatial degrees of freedom using the Lawson procedure. The Green's function terms are expressed in Jacobi coordinates using equations 20 and 21, which are valid for any intrinsic state of the target. The authors emphasize that equation 21 does not restrict the target state to no CM motion in the reaction dynamics but rather is a mathematical equality that uses only wave functions free of CM excitations to exactly connect the SANCSM calculations to the transitionally invariant T.I. counterparts that can be calculated in Jacobi coordinates. The authors use the completeness relationship in equation 22 to express the Green's function in an operator form. They define the T.I. Green's function terms, which are given by equation 23. The T.I. Green's function is calculated using the last part of equation 23, which can employ any many-body method with laboratory coordinates and the Lawson procedure. In the following pages, the research discusses the translationally invariant Green's function for spatial spin degrees of freedom, focusing on the regimes E greater than epsilon plus and E less than epsilon minus. For E greater than epsilon plus, the problem is solved in the A+1 CM system, using the cluster basis states with no CM excitations. The Green's function is calculated through EQ 27, which involves the use of the Lawson technique for the whole part. This regime's T.I. norm is calculated through the particle norm, NP, and the whole norm, NH. For E less than epsilon minus, the problem is solved in the A-1 CM system, and the Green's function is calculated using EQ 31. The T.I. whole norm is calculated through the imaginary part of the Green's function integrated over the energy range. The research emphasizes the importance of orthonormalization and removing CM spurious motion in the cluster basis states to ensure accurate calculations. The summary highlights the novel ideas and significant findings presented in the research, including the novel approach to calculating the T.I. Green's function and the importance of considering CM effects in heavy target reactions. The authors develop a novel approach to calculate the Green's function for nuclear many-body systems using the Langr method, which is a crucial component in nuclear reactions and spectroscopy calculations. They employ the no-core shell model with similarity renormalization group evolved chiral potentials to compute the Green's function. The Langr algorithm is used to calculate the Green's function matrix elements, represented as a continued fraction evaluation, and a projection method is applied to remove center of mass excitations from the cluster basis states. The Langr vectors are orthonormalized, and the completeness of the Langr vectors is inserted into the calculations. The Green's function is computed using the Layman representation, and the Langr method is used to evaluate the continued fraction. This approach is demonstrated to be more efficient than the traditional method of calculating the Green's function using the eigenvectors of the Hamiltonian. The authors apply their approach to the Fourier, Fourier elastic scattering reaction and compare their results to experimental data and other ab initio theoretical studies, showcasing good agreement. The authors also utilize the ab initio SANCSM, GF approach to calculate neutron Fourier scattering phase shifts and optical potentials, demonstrating a remarkable agreement with experimental data for laboratory kinetic energies. ELAB is less than or equal to 12 MeV. The calculated spectral functions for Fourier provide insight into the single particle properties of the target nucleus, and the spectroscopic factor S is calculated using both the trace of the norm of the whole states and the overlap contribution. The study of the epsilon dependence and imaginary contribution of the optical potential reveals that epsilon has a negligible effect on the phase shifts calculated in the SANCSM, GF method. The research paper introduces a novel approach to constructing ab initio nucleon-nucleus, optical potentials using the symmetry-adapted no-core shell model, SANCSM, and the Green's function, GF, method. This approach provides a tool to describe nucleon-nucleus interactions, enabling the calculation of spectral functions to probe correlations and single particle properties of the target nucleus. The SANCSM, GF method is demonstrated in the development of ab initio translationally invariant optical potentials for the n+4 system, which evaluates the single particle time-ordered Green's function starting from realistic internucleon interactions. The study focuses on n+4 elastic scattering, providing a total cross-section that reproduces almost all data points within 1 sigma and is reasonably independent of h omega. The phase shifts calculated with infinite space energies agree with other ab initio theoretical studies, highlighting the importance of resonance energies and correlations in reproducing the n+alpha dynamics. The results suggest a reliable parameter-free null optical potential for energies up to E tilde operator 12 MeV. The study also discusses the dependence on model space parameters and infinite space energies, emphasizing the need for convergence studies with respect to n-max. The paper concludes by noting the potential for this approach to inform phenomenological non-local optical potentials and provide insights into short and long-range correlations. The method can be applied to a broad range of nuclei accessible to the SANCSM, currently up to the calcium region, and has implications for proton elastic scattering of heavier nuclei, and generalizations to deuteron elastic scattering and inelastic scattering. The paper discusses the development of a microscopic structure-based optical potential for predictive calculations in nucleon-nucleus scattering, leveraging ab initio theory and the few-body approach. It utilizes symmetry-adapted no-core shell model, NCSM, wave functions and chiral nucleon-nucleon, NN, and 3-nucleon, 3N, forces. The importance of incorporating translationally invariant theory and antisymmetry in the nucleon optical model is emphasized to ensure accuracy in the calculations. The study also highlights the role of clustering in the structure of light nuclei using the resonating group structure method, providing insights into the nucleon-nucleus mean field and the impact of clustering on the 8 Li beta decay and recoil form factors. Furthermore, it explores the use of the Faddeev-Jakubowski equations for calculating the nucleon-nucleus scattering, as well as the application of the ArXiv matrix theory in analyzing neutron scattering from the hydrogen and helium isotopes. Additionally, the work introduces a novel method for the elimination of spurious states in the nuclear harmonic oscillator shell model, utilizing group theory and special symmetries in nuclear physics. This method is essential for precise calculations of electromagnetic sum rules and recoil form factors, which have implications for understanding the structure of nuclei. The authors also reference several key studies on nucleon-nucleus scattering, including the importance of the nucleon optical potential and its connection to the nucleon-nucleus mean field. They emphasize the need for benchmark calculations of neutron-deuteron scattering cross-sections using wavepacket continuum discretization and chiral NN interactions. Finally, the paper outlines the significance of microscopic theory in the elimination of spurious states in the nuclear harmonic oscillator shell model, which is crucial for accurate calculations of electromagnetic sum rules and recoil form factors. The study concludes by highlighting the importance of incorporating translationally invariant theory and antisymmetry in the nucleon optical model to ensure accuracy in the calculations, as well as the role of clustering in the structure of light nuclei using the resonating group structure method.